Hello everyone, welcome to our organic chemistry family. Today I want to introduce you to my family members. Meet them. First we have alkenes, alkynes, benzyl ring, aromatic. Smells so good. Amines, alcohol, ether, alkyl halide, thiol, aldehyde, ketones, ester, carboxylic acid, and amide. And I'm going to introduce you one by one. Alkane, yeah, extremely very strong and mighty. Okay, never give up. They are very unreactive. And this is how they look like. They have a carbon-carbon single bond. As for alkenes, they have carbon-carbon double bond, and they are less, not as strong as alkane, but more reactive because they have a nucleophilic part here. And next we have alkyl halides, which we usually describe them as RX. R is for the alkyl group and X is for the halide group. X can come from any of the halogen, like F, Cl, Br, and iodine. And we have alcohol. What's so special about alcohol is that the C is bounded to the hydroxyl group. C is bounded to the hydroxyl group. And next we have the thiols. Thiols, we have garlic. We smell it, the stinky garlic smell, the rotten egg smell. Then it's thiol. And thiol, what we have is SH. So R bounded to S and H, then it's what we call thiol. And when we have it as a substituent, we call it mercaptan. As for aldehyde and ketones, what's so special about aldehyde is that for the carbon, this carbon is double bonded to O, and the same carbon is also bonded to H. But for ketone, the H is replaced with another R group, another alkyl group. And next we come to amines. So what's so special about amines is that we have a nitrogen atom. So this is what we see at ammonia here. And whenever we have an R group binding to nitrogen, we call it primary amine. 2 R groups, secondary amine. 3 R groups, tertiary amine. And next we have ether. So ether is ROR. So between two alkyl group with an O bounded to 2 alkyl group, then we call it ether. Carboxylic acid and derivatives. So this is what we call carboxylic acid. What's so special is that they have a COOH, a carbon double bonded to a O and single bonded to hydroxyl group. And the derivatives are acid halide, acid anhydride, ester, and amide. And we also have a nitrile, a carbon triple bonded to a nitrogen. That's what we call nitrile. And yeah, one of the example is as for acid halide, acid acyl chloride. So the X here, we have a Cl. And that's why we call it acyl chloride. It's pretty important. We need them for a lot of reactions. Anhydride, 2 carboxylic acid combine and lose water. You notice there's no OH here, and that's what we call anhydride. Ester. Ever wonder why your mother's perfume is so nice? It's from ester. COOR. So instead of having a H here, we have another R group here. Amide. What's so special about amide is that C double bonded to O, and the C also single bonded to nitrogen. As for nitrile, as we said previously, C is triple bonded to a nitrogen. So let's see the reactions. How do we prepare alkenes? Alkenes are so unreactive, but we can prepare them from alkenes through hydrogenation. We introduce nickel and hydrogen gas, we get alkanes. What are the chemical reactions? Combustion. So when we introduce energy, such as electric energy or any source of energy, we can actually break down alkane to form carbon dioxide and water, and it's very exothermic reaction. We also can undergo halogenation, in which we introduce UV light and halogens, such as fluorine, chlorine, bromine, iodine, and therefore, this alkene can undergo substitution to form a series of products. And products can undergo continuous substitution until it's fully substituted. It's no longer an alkane, but it's alkyl halide. Next, we come to alkene. So how do we prepare alkene? We can actually remove the water and alcohol, dehydration of alcohol. So with the introduction of acidic environment, concentrated sulfuric acid, we can turn it into alkene. Next, we can also eliminate the alkyl halide. How do we eliminate? So elimination comes in two ways. We have E1 and E2. Depending the strength of the base, if we use a stronger base, then it undergoes an E2. And then also depending on the carbon, whether it's a primary, secondary, or tertiary carbon, then it depends, then decides which reaction it should go. And we get an alkene. Chemical reactions of alkene. So there's three types. First is the hydration to form alcohol. Second, addition of hydrogen to form hydrogen halide. Third, hydrogenation of alkene to form alkane. I think this we mentioned just now. So how do we make alkanes? We choose alkene hydrogenated and we get alkane. And hydration of alcohol. So how do we actually add water back to alkene? Just now we took it away from alcohol. By three methods. The first method is that instead of using a concentrated sulfuric acid, we use dilute sulfuric acid. And this is what we call acid catalyzed hydration. Second, we can undergo oxymercuration and demercuration by introducing this reagent here. What's so special about this reaction compared to our first one is that the intermediate does not undergo carbocation rearrangement because this reagent is very, it creates steric effect. And the last one is hydroboration oxidation, in which we there's no Markovnikov addition, which means that the hydroxyl group is not added to the most substituted carbon. Instead, it's added to less substituted carbon. And these are the reagents involved. Addition of hydrogen halides. So hydrogen halides, we can add them to the alkenes by introducing the acid form of the halides. So we can have two ways. First, Markovnikov addition, in which we add the halide group to the more substituted carbon. If we wanted to do the opposite, to add it to the less substituted carbon, we introduce ROR with HBr. This Br could be replaced with Cl or I, depending on what halide we want to add onto the group. And this we mentioned previously. Alcohol. So alcohol, how do we prepare alcohol? First, we can use reduction of carboxylic acid and derivative, such as ester, anhydride, and acid chloride. We usually use LiAlH4 to do reduction. Next, we can also make tertiary alcohol with Grignard reagent. So by using ketone and acyl chloride or ester. This is an example of using ester. So introduce Grignard reagent, which is this, and it could undergo, it adds a OH group here and to alkyl group, making it a tertiary alcohol. Addition of alkene to alcohol. We mentioned previously, three ways. Chemical reaction of alcohol. So alcohol can undergo oxidation through potassium dichromate. So we usually have a primary alcohol, and then we introduce this reagent, and we can oxidize it to form carboxylic acid. The intermediate will be aldehyde. But what if we have a secondary alcohol? Then we can use it to form ketones. For tertiary alcohol, it's very unreactive. And we can also dehydrate the alcohol. Depends what environment we use. If we use a very basic environment, we'll get ether. If we use in a very acidic environment, we get alkene back itself. And also depending on the temperature introduced. And next, we can undergo esterification. We get perfumes through alcohol by introducing acid, carboxylic acid, different types of carboxylic acid in an acidic environment. Then we get esters. Alcohol can also undergo nucleophilic substitution, remove the hydroxyl group and introduce the X group. So we can use HX, PBr3, or SOCl2, depending on what we want to add here, to form alkyl halides. Remove the OH, introduce the halide group. And next we come to thiol. So how do we make thiol? Same, we can remove the X group from RX and introduce the SH group, the thiol group. This is how we undergo substitution. And notice that in this substitution, the whole molecule undergoes inversion configuration. And chemical reactions of thiol. These are the chemical reactions of thiol. We can undergo oxidation of thiol to form disulfide. And these are the reagents involved. Disulfide 2S, there's no H here. And aldehydes and ketones. So how do we prepare all these things? Preparation of aldehydes and ketones. So as we mentioned previously, primary alcohol can make carboxylic acid and aldehyde into intermediate. So we need aldehyde. So we need to remove carboxylic acid, but not really removing here. We use a weaker weaker reagent here. So instead of using K2Cr2O7, we use PCC, CH2Cl2, which is PCC is pyridinium chlorochromate, and CH2Cl2 is what we call dichloromethane. And that's how we get aldehyde. But how about ketones? Well, ketones, we can just use secondary alcohol. We can also form aldehyde through reduction of acyl chloride and anhydride. And you notice that previously reduction, a usual reduction will be LiAlH4, but here we introduce a third butoxide butyl group, so it's not that strong, and therefore reduce it to aldehyde instead of alcohol itself. Chemical reaction of ketones. Ketones can carry out a lot of chemical reactions. You can see this table. It can react with in an acidic environment to form a diol, acidic environment with the introduction of alcohol to form acetal. Acidic environment to react with diol to form a cyclic acetal. Acidic environment with a dithiol to form a cyclic thioacetal. And react with different types of amines, primary amines to form imines, secondary amines to form enamine. This is enamine. And it can even react with hydrazine to form hydrazone. One thing I want to point out here is that this thioacetal can actually reduce to alkene to form renane-nickel. So we now know, instead not only through alkene, through hydrogenation, we can form alkane, but also renane reduction, cyclic thioacetal through reduction of renane-nickel, we can also form alkane. Of course, alcohol through LiAlH4, and also through green type reagent. And last but not least, we have it react with carboxylic acid to form esters. And this is what we have with ketones. So I want to point out this Wolff-Kishner reduction. As just now, ketones, we can actually react with hydrazine to form hydrazone. And we can actually reduce it to alkanes by introduction of potassium hydroxide with heat. Amine. So how do we make amine? Amine are so important. We need it for our survival. We need to make amino acid. Amino acid is required for proteins, to make proteins in our body. So there are 5 ways of making amines. First is from the reduction of nitriles. Second, reduction of amides. Third, from alkyl halide and ammonia. Fourth, from azide synthesis. 5, from Gabriel synthesis. So reduction of nitriles. From nitriles, we can undergo reduction to form amines. And how do we prepare nitrile? We can use RX, which is alkyl halide, introduce sodium cyanide, undergo SN2 to get nitriles. Next, we can also undergo reduction of an amide. So amide undergo reduction to form amine. How do we get this amide? We can introduce carboxylic acid react with SOCl2 and NH3, which is ammonia, to get amide, and amide can be reduced. Reaction between alkyl halide and ammonia. So alkyl halide react with ammonia and form a series of amines. You can see here it can form primary amine, secondary amine, tertiary amine, quaternary amine, and it's just a glob of a lot of different things, a lot of mixture in this. So we want the reaction to be clean. We want only primary amine. Then what should we do? We use azide synthesis. So in azide synthesis, we use alkyl halide introduced with NaN3. Then we form this thing, and it undergoes hydrogenation to form this amine. Instead of using hydrogenation, we can also use reduction to form amine. And next, Gabriel synthesis, where phthalimide undergoes potassium hydroxide, react with potassium hydroxide to form potassium phthalimide, and potassium phthalimide can undergo SN2 with RX, alkyl halide, to form this compound. This compound can be acidified to remove the NR here. And therefore we can get, we can actually introduce some base to neutralize this, and therefore getting an amine. Chemical reactions of amine. So amine can react with acyl chloride to form amide, as mentioned previously. And also it can react with ketones to form imines and enamines. And this is what we talked just now. And ether, how about ether? ROR. How do we prepare them? There's two ways. First, Williamson ether synthesis, in which we introduce sodium hydride and then alkyl halide to form this. Next is alkoxy demercuration, demercuration. So what's so special about this alkoxy mercuration, demercuration? Remember in alkene, we also use this to form alcohols. But what's so different here is that to form, now we want to form this ether. Instead of using water, we use ROH here. So we get an ROR group, and this is undergo Markovnikov addition, which means the OR group is added to the more substituted carbon. Carboxylic acid and its derivatives. So how do we make carboxylic acid? There are two ways. First, we can let alkyl halide react with sodium cyanate to produce a carboxylic acid. We can also use a Grignard reagent, also with alkyl halide. Next, I would say just now we can use alcohol, oxidize it to form carboxylic acid. Chemical reactions involved. We can reduce it to form alcohol. We can also form amine, and then amine. So as said previously, we can use SOCl2 and ammonia to make it an amide, and amide can be reduced to form an amine. Acid chloride. So acid chloride, these are the reaction of acid chloride. Why do we need acid chloride? Because sometimes you see that the reaction of carboxylic acid is actually limited. So we convert it to acid chloride by using SOCl2 and let it to undergo a series of reactions to get what we want. It's especially useful in synthesis problems. So in acyl chloride, it can react with pyrimidine and hydroxides to form ester. It can also react with ammonia to form primary amide. This primary amine to form secondary amide, and secondary amine to form tertiary amide. Moreover, it can also undergo reduction, just like carboxylic acid itself, to form alcohol, and partial reduction by introducing a third butoxide group in this LiAl to form aldehyde. It can also undergo Grignard reagent to form alcohol and Gilman reagent to form a ketone. What's different about Grignard and Gilman is that Grignard, we actually get two R groups at the product, but for Gilman, there's only one R group. Phenylhydride is actually pretty similar with the one mentioned before, acyl chloride. So we still get ester and all the amide with using different amines. And also alcohol, reduced alcohol, aldehyde, and ketones with also forth. Ester. So how do we make ester, the perfumes? First, we can use acid chloride react with methanol to get the ester. This methanol could be changed to other different types of alcohol depending on what type of ester you would like to make. Chemical reaction of ester. So ester can undergo acid hydrolysis, which means we introduce of water, which means we introduce acid, and we get a carboxylic acid. You can also undergo base hydrolysis or saponification to get your soap. So we introduce sodium hydroxide to get this. And then we also introduce some acid to neutralize it. And so this is our whole family of organic chemistry. We have covered this throughout the past 20 minutes. I hope you enjoy it. Remember to like and subscribe. Thank you.